Our final speaker of this session is Thomas Rolinger from the University of Maryland, and he will be presenting a talk entitled Automatic Adaptive Prefetching for Fine-Grained Communication in CHIUW. Take it away, Thomas.
All right, thanks for the introduction. So this work is part of a larger project that I've been doing for a little while on addressing fine-grained communication in CHIUW. So this talk is more or less just an advertisement for part of that. So first, going into some motivation, what is fine-grained communication? Where does it kind of show up, and why is it an issue? So to motivate this, here is an example of PageRank, which is a graph analytic. This is written in CHIUW. It's both shared and distributed memory parallel. It exhibits a lot of nice high productivity features that CHIUW provides, but of interest to us for this talk is this memory access on line 5. So G is a distributed array. It represents the graph data structure, and we're making this irregular memory access to it. But because G is distributed, this is what's going to lead to fine-grained communication, which means we're sending a bunch of small messages over the network, which is a problem because we're better off sending fewer larger messages if we can. It's also worth noting that this type of access pattern is not specific to just graph analytics. You would also see it in different types of scientific computing applications. But the main problem that we want to address here is the performance of this code. While it's really easy to write and read, it doesn't achieve very good performance. So this is showing runtime scalability from 2 to 32 locales. And we can see that it doesn't really scale. It's pretty much flat from 2 to 32 locales. So the takeaway here is the fine-grained communication that's exhibited in this application is leading to our task essentially stalling all the time, waiting for data to arrive over the network. So kind of the moral of the story is just because you have this high productivity code, it doesn't necessarily mean you're going to get the performance you would expect out of it. So what I want to talk about here is how we can achieve better performance for these codes with these access patterns without having to sacrifice or lose the productivity that CHIUW provides. And one way we can do that is by optimizing the code, but doing so automatically so that the user isn't actually responsible for modifying their code to do the optimization. So here's the outline of this talk. I will go over the optimization itself, which is adaptive remote prefetching. I'll then spend a couple minutes talking about how we implement this as a compiler optimization. So this is how we apply it automatically. And then I'll wrap up with some performance results. Okay, so first the optimization. We're doing prefetching, so it's worth just making sure people know what it is. So prefetching is a technique that we can use to hide communication latency by overlapping it with other communication or computation. So the idea is we're issuing non-blocking reads for some remote data that will be needed in the future. So rather than having to sit there and wait for it to arrive, we can continue our program doing something useful. And then whenever we need that data, it will already be there available locally so we can access it faster. So we can kind of see this in a simple example. Here is a for all loop with one of those irregular access patterns. This is an example of like an index gather type of operation. So if we didn't have prefetching enabled, we can imagine that each iteration of this loop is going to issue a fetch for A at B at I, and it's going to have to stall and wait for that remote data to arrive over the network. With prefetching, what we would do is still issue the fetch in the first iteration for A at B at 0 and stall, but we'd also be doing this non-blocking fetch or prefetch for A at B at 2. So we're looking 2 iterations ahead in the loop. The idea is when we get to the iteration where I is equal to 2, we don't have to wait for that remote data. It's already been prefetched. It's presumably in some sort of cache, and we can access it faster. So that's the main idea behind prefetching. It's worth mentioning that there is this idea of a prefetch distance. This is the look ahead factor. How many iterations ahead in this loop are we trying to issue a prefetch for? This example uses a prefetch distance of 2. But the question is, what value do you pick, and what factors actually determine your decisions in picking this value? Another thing to talk about is what are we prefetching into? On the last slide, I mentioned the idea of like a cache, but in this case, we're not prefetching into a processor or CPU cache. We're going into CHIUW's remote data cache. As the name suggests, this caches remote data on a locale, and it's a software managed cache. And the way it works is that each core, or a task, if you want to think of it that way, on a locale has its own remote cache. Therefore, each task that's doing a for all loop will have its own independent prefetch distance that it's managing, and we'll have to determine what this prefetch distance should be independently from the other task. So you could think of having many caches that we have to manage independently here. Okay, so talking about the prefetch distance, how do we actually pick a good value for this? It turns out that this is very difficult to do statically offline without having information about what the program is actually doing. These memory access patterns, because they're irregular, they're data dependent. We don't know what they are until we're running the program. So even if you pick a good distance that you think works well to start with, it may not be what you want to use throughout the entire program. The access pattern could be changing. Furthermore, if you were to run a different data set or a different workload, or even just run on a different system, your analysis that you did to pick this prefetch distance may change because of these different parameters that determine, for instance, things like the network latency, which determines how fast or how far ahead you should be prefetching. So picking this value offline is very difficult. It's a moving target. So our approach is to do this adaptively. So we're going to be increasing or decreasing the prefetch distance as the program is running. So if we're doing it at runtime, we can actually use information that we know about the access pattern, as well as monitor how well our prefetches are going. So how many did we issue and how many of them came in late? A late prefetch is one that hasn't completed by the time we get to actually access that data. So we're still stalling, waiting for it to arrive. So in that case, for instance, we would want to increase our prefetch distance so that in the future, the prefetches would have a bit more time to finish so we don't have to wait for them. So that's the basic idea of this optimization. There's a lot more detail that goes into it that I won't have time to present here. But moving on, I want to speak briefly about how we can do this within a compiler. So again, the point is applying this optimization automatically will allow us to not have to sacrifice any productivity benefits that CHIUW provides from manually modifying our code. So the first step in doing this as a compiler optimization is static analysis. So we've added some passes to CHIUW's compiler to automatically identify potential sources of fine-grained communication. And we're looking at these within for all loops. And we're looking for patterns that look like A at B at I. So A and B are arrays, and we require in this case that A is a distributed array. So if A is distributed, then we're likely to have some remote communication. And when we have this indirect access pattern, it's also likely to be fine-grained. We also have some static checks that try to reason about the for all loop itself and how their iterations are actually progressing from iteration to iteration. I won't have time to go into details, but this is important when we're doing bounds checking to make sure we're not prefetching outside of the bounds of the array itself. So once stack analysis is done, we have a candidate for what we can prefetch. Then we have code transformations. So we're going to take the code as it's being compiled and modify it by adding some variables to do bounds checking. We're going to have to create the prefetch distance variable itself. We have to actually implement the bounds checking, add code that's going to be kind of periodically trying to adjust the prefetch distances using the runtime information. So there's a lot that goes into actually modifying the code. And that's kind of the takeaway here is that you don't want to do this manually. It will decrease your productivity. So that's why we want to rely on the compiler to automatically do this optimization. And again, there is a lot more details going into the compiler side of this that I'd be happy to talk about offline. Okay, so moving on, I want to now talk about the performance of this optimization. I looked at two different workloads, both graph analytics. So again, this optimization is not specific to graph analytics. I just happen to have a fair amount of these workloads already implemented, so it's just easier for me to start studying them. So we have PageRank and SSSP, which is single shortest path. Their kernels are shown on the right in CHIUW. As you can see, they're pretty concise, easy to read, using all the productivity features that a language like CHIUW provides. And then we have the data sets we ran on. These are the different graphs. The first three graphs there are from the Graph 500 benchmark, so they're synthetically generated. And then the remainder of the graphs are from the sweet sparse matrix collection, and they are real graphs. As far as the systems, I ran on 3 different clusters. 2 of them are InfiniBand and 1 is a Cray. So the purpose of evaluating 3 different systems is to see how well this optimization can actually adapt to changing environments. The point of adapting the distance was that we can respond to things like a different network interconnect, which would have a different latency. So we'll be able to see how well we're actually doing on 3 different systems and on 2 different workloads. So here are the results for PageRank on the top, and then SSP below that. These are runtime speedups over the baseline being the original code where we didn't have prefetching enabled. I'm showing each workload for the largest graph I evaluated, just because it's a little bit easier to visualize this rather than showing all the results on one slide. So higher bars here mean better performance. And just want to point out that the speedups can be pretty significant, 3.2x on PageRank and 1.7x on SSSP. And the overall runtimes of these workloads are actually fairly substantial. So these speedups are leading to pretty large reductions in the runtime. But beyond just the speedups, I wanted to look a little bit further at this optimization and try to answer the question of whether adapting the distance is actually helping. Are we actually adapting it as the program is running, or are we just getting lucky and finding a distance that works well and using that throughout the entire program? So to do this, I looked at how many prefetches we issued with each prefetch distance that was used throughout the program. And we can represent that as a heat map. So this is the map for SSSP. And the way to interpret this is that each row in the heat map is one of the cores on the system. I think I was using about 8 locales here, so it's 20 cores per locale. And again, each core has its own remote cache, therefore its own prefetch distance that's independent of the other cores. And each column in this heat map represents the different values we use for the prefetch distance. So the brighter that something appears in this heat map, it means the more prefetches we issued with that distance from a given core. So for instance, if we look at this bright column, it says that at some point, majority of the cores were favoring a distance of 12. So that's what they were using for the most part throughout the program. So we can do this experiment on the other workload and the other systems, and we can see these patterns. I'm not going to go into details of each individual heat map here, but the point of showing them is we see 6 different patterns across 3 different systems and 2 workloads. So qualitatively speaking, we are seeing something happening with adapting the distance. We are changing it throughout the program. We do tend to find distances that work well and stick with those, but we can see that we are also using other distances throughout different phases of the program. But one thing we can look at is whether we would be better off just picking a static distance to use up front and keeping that constant versus adapting. So we can kind of do what we did on the last slide, which is look at these heat maps and extract the most preferred distance that was used, and then use that and see what happens. And it turns out that that's never better than actually adapting the distance. In the worst case, it's up to 44% slower than actually adapting. So this is quantitative numbers showing us that actually adapting the distance is the better thing to do in this case. We're able to adapt to the different memory access patterns and the different system environments. So some discussion in future work. I'm looking at more sophisticated heuristics to adjust the distance. What I have now is pretty simple, but it's kind of simple by design. We're going to be doing this distance adjustments many, many times as the loop is running. So we want to make sure that it's fast and not slowing the program down. Also, there are some tunable parameters that we use in this heuristic. For instance, how often do we kind of pause a task for it to adjust its distance? And what is the tolerance we have for late prefetches before we decide we need to actually change the distance? I've done sensitivity studies for these parameters on the different systems and workloads and picked ones that worked well. They're not all that sensitive, but there could be more intelligent approaches to doing this, like auto-tuning. And last, evaluating more architectures and systems and workloads would make this work a bit more interesting, so we can see actually how well does it scale or adapt to different environments.
So Thomas, we have about 3 minutes left if you can wrap up for questions.
Yep. So here's a summary to show where we are. So we started with that blue line, which was the poor performance of PageRank due to the fine-grained communication, and the orange line showing what we're able to achieve with adaptive prefetching. And again, this was applied automatically by the compiler. So we essentially took the same code that achieves the blue line performance and just recompiled it and was able to achieve the scalability we see in the orange line. And with that, I can take any questions.
Looks like we have one question from Chris Long. Chris, can you go ahead and speak? I'm not hearing Chris, so maybe there's a microphone problem. There's a question in the chat from David. Being a bit detail obsessed, I'm impressed, surprised that your example on the motivation side performed as well as it did. I would have imagined performance would fall with more locales unless perhaps CHIUW is smart enough not to distribute when it hurts. I also note that you started your graph with 2 locales, so perhaps the 1 locale performance was much faster than 2, and I'm not really sure what the question is in there, but
yeah, it's performance definitely hits a cliff from 1 to 2 locales. It's because you're just going to be paying the communication cost, and especially for this type of application where you're communication bound. So I typically don't start with 1 locale as a comparison point because it would skew the rest of the results in terms of showing it on a graph. But definitely running 1 locale is generally always going to be faster in this case, until maybe you reach enough locales where you're seeing scalability. But as we see in this chart, it doesn't look like we're going to get any scalability anytime soon with the unoptimized code.
So you don't know on this last one then how this, or you maybe do know, but it doesn't show here, how this compares to just running on 1 locale?
Yeah, I don't have the results here, but I would guarantee that the one locale performance is probably better than anything else on this chart.
Right, but
It's
presumably if
definitely
it's PageRank, your data set size is so big that you probably can't run on one locale. So there's still a compelling case for distributing, and you want to do it well.
Yeah. There's definitely graphs I've ran that won't fit on anything more than 2 or 4 locales, and of course it depends on your system. Some systems have less memory per node than others.
Yeah, great. Thanks so much.
Looks like we have a couple of additional questions in the chat, but before we get to those, I want to note that we've reached the time for our 15-minute break. But the discussion can, of course, continue if people want to stick around. After the break, my close friend and colleague, Paul Hargrove, will be delivering our keynote address, and I encourage you all to return at 10:30 Pacific and heckle him. And until then, I invite folks to unmute and engage with discussions with the speakers. Looks like one of the questions in the chat is, did you run any experiments with copy aggregation and how that would factor in? This is something I was also curious about.
Yeah, I didn't, because as it stands, the way the code's written, I'm not sure if the copy aggregation as it's implemented right today would actually be applicable. It's not as simple as a reduction that needs to be done typically. So I have done other aggregation-based optimizations, just not for PageRank, because I don't think off the top of my head that's actually a good fit for that optimization itself. Replication is a much better choice there, because PageRank is iterative. You do the same kernel every single time and the access pattern doesn't change. You're better off just replicating all your remote values before you start the kernel and then just accessing those locally. And I have some other work prior to this that shows how that does.
So Thomas, have you considered adjusting your heuristics based on locality? So how would your heuristic handle a loop where a large fraction of the sparse accesses were to the current locale, but a smaller but unpredictable fraction were remote, where presumably prefetching would only be profitable in the latter case?
Right. That's something I actually just started looking at because I did run into some data sets where that's certainly the case. And with it stands now, prefetching starts to hurt you actually. The overhead of doing the prefetches for data that I guess that you can call it's useless prefetches because it's already in the cache or already local. And it's not even prefetches for data that's already local. If you have a fairly sequential remote access pattern, CHIUW's remote cache will do a pretty good job of reading ahead. So I've been looking at detecting kind of when prefetches are in that state and then essentially backing off and just not prefetching anymore. But it's a little bit tricky, and it adds some more tunable parameters for, what is your tolerance for how many prefetches you issue that aren't going anywhere? And, do you start back up at some point to try to prefetch again? So it's a little bit tricky, but I have been looking at some of those factors.
Have you considered any more aggressive transformations that would dynamically reschedule the loop iterations based on prefetch arrival?
I have not looked at that, no.
Okay. We have another question in the chat from Benson of whether you've done any measurements on Rocky, Ethernet hardware, network hardware.
No, I've been purely on InfiniBand, FDR, HDR, and on the Cray Aries.
There was a question from Kevin. Did you see any significant perturbations in runtime prefetch distance depending on job placement, network topology, or system size?
Not so much, but that may be because on the systems I've had access to, they're not that busy, I guess. So I tend to get kind of the same nodes every time, or I'm not really contending with any other jobs. But that could definitely be a thing depending on the topology of the network and where your nodes are placed. If you get unlucky and have nodes that are spread across switches or something like that. But hopefully the adaptive nature of the optimization should be able to detect that and adapt the distance to account for any increase or decrease in latencies.
Cool. So I might have missed some questions in chat, so feel free to unmute folks and ask the speaker additional questions while we're sitting here on break.
Hi, Thomas. I have a question for you.
Sure.
You were showing a speed up of, maybe up to, I think it was 2 or 3 X in some cases. My question was, do you expect that speed up would increase as you went to higher scale?
Scale with locales or data set?
Yeah, number of locales. Like if you ran on 1,000 locales, like in, one of the Elliott runs.
Yeah.
Would you see much bigger speed ups, or would it stay around 2 to 3X?
Hard to say. I would I would hope to see perhaps some increases because if your data is getting even more distributed, then hopefully you have even more remote accesses. And so if it would hurt the baseline in that regard, then I would hope prefetching would also get kind of a inverse proportional increase in the speed up, but not entirely sure. I do have a bigger system now in our lab that has 128 nodes, so I'll at least be able to push up to that scale. And we'll see what happens.
Thanks.
Yep.
Thomas,
Chris,
I don't know if you or anybody else in the chat has a sense of when you start to see that drop off in the baseline, because it sounds like this touches on the question of why it's so flat when you went from 2 to 16 maybe, or 32 in your motivation slide, and it didn't really drop as I would have naively guessed it would, as instead of half, we went up to 7/8 or 15/16 of the data being remote rather than local.
Yeah, so I think there's a bit of trade-off with, as you increase the locales, you are adding more compute, and PageRank has some compute involved. So it really depends on how the data is getting distributed. Now this is a block distribution, so it's pretty standard the way it's going, but you should be getting, if you ignore communication, you should obviously get faster by adding more compute to speed up the computation. But the slowdowns we're seeing are due to communication, and I guess as we go from smaller to higher locales, it's not necessarily dropping off every time. You are getting a benefit from accelerating some of the compute. And just, I think the reason why we don't see the scalability is because the compute is just not a significant part of the overall computation or the workload of the kernel.
Of course, yeah. Your original. Chris, go ahead, Dan.
I was going to say, Chris Long has typed a couple questions in chat, but have you been able to fix your mic? Are you able to speak now, or should I read your questions? Okay,
he might be just dialed in.
Isn't working.
Yeah, I can see the questions, I think.
Yeah, he says the frontier for PageRank doesn't change dynamically as it does for BFS or say SSSP in the push direction. Would you expect to see better speedups for adaptive prefetching distance on those workloads versus PageRank?
Right. So I have SSP results, and the speedups aren't as high. And for that reason, it's because when you compare the two workloads, just from a kind of lines of code, SSP is much more complicated. There's actually 2 irregular memory accesses in the SSSP kernel. Only one of them is a candidate for how we do prefetching. So you're not going to get as big of a boost relative in terms of speedups on SSSP because there's another kind of bottleneck. But that access can be aggregated, and I have another optimization that can also do aggregation automatically, and it doesn't get in the way of prefetching. So when you apply both together, then you get a net speed up versus what you would get with just one of the optimizations applied.
He also asks, it looks like you were implementing PR and SSSP in the pull direction, yes, and that makes intuitive sense if you're prefetching, but would you expect some benefit for a push implementation? And have you benchmarked against a push implementation?
Right. I haven't done push mostly because maybe just because I don't know how to do it correctly, but it seems like it's a much more kind of messy approach to implement, because with the pull direction, I can do the updates to the PageRank values without having any explicit synchronization. So I have read versions that we read from the prior iteration, and then we update the write versions. With the push direction, we would have to push the updates, and I think that would require atomics of some sort. So I've just kind of stayed away from that in general, just because for the scope of the work I do, which is mostly taking kind of textbook, easy to write algorithms and trying to automatically improve them, I haven't explored the more complicated push direction.
Okay. I should also, I guess I forgot to call for clapping hands for Thomas, but thank you very much for giving a great talk. And obviously there was a lot of audience interest and engagement in that. And thanks for sticking around for the extended grilling section here.
Yeah, no problem.